Hey everyone. Oh, whoa. Nope. Everyone, we'll get started in a second. So feel free to get your pizza and sit down. See you, Diane. So hi. Thanks for being here. So welcome to our November meetup. As always, thanks Mozilla for food and the space and everything. Just one announcement. The Rust 2018 edition is being released soon, and you should help test it. It's got all these goodies like better pads and eventually async await. Also, Clippy's better in the edition. Yes, that's happening. Non-lexical lifetimes are happening, finally. After years of saying it's coming, they're happening. For real this time. I promise. All right. If you have any talk ideas for future meetups, you can email me at this. We have meetups here in the South Bay. We try to alternate. But yeah, if you email me, I can connect you to whichever meetup you want. Today we have two talks, which are in the wrong order here, but we have Robert talking about Flatbuffers in Rust, which is a serialization framework, and we have Raph talking about low latency music synthesis. So let's give it up for Robert. Yeah, sure. I don't know how to switch. I don't know how to exit that. Aha, just close that. Oh, sorry. You want me to? F12? Oh no. No, come back. Okay, I don't know how to do this.
I think there's, if you click on the square down there.
Oh, there it is.
Yeah.
It's been a while since I've been on the Mac. Anyway.
Thanks. Hi, everybody. I'm Robert Winslow. I'm going to talk to you tonight about Flatbuffers in Rust. But I'm going to start off with some cheesy jokes. Forgive me, I don't normally do this, but there are two of them. One, a hamburger walks into a bar, bartender refuses, says, "Sorry, we don't serve food here." Yeah.
I like that. Very good. Excellent.
All right. Second one, an SQL query walks into a bar and sees two tables. He walks up to them and says, "Can I join you?" So I know you've just had a bunch of pizza and beer and you've had a long work day, so that's just to lighten the mood a little bit. So if I could get a show of hands, who here right now thinks that serialization is exciting? Hey, that's pretty good, actually. I'm surprised. Well, I hope I can convert the rest of you. So here we go. This is my hope for you at the end of the talk. You'll feel like this. So here's the agenda. I'm going to do a little introduction. I'm going to set the stage with a little bit of talk and opinions about serialization, explain why Flatbuffers exist, because there's a whole lot of other choices, how you can use it, how it works, how we test it, and then what there is still to do. My name is Robert Winslow. I'm an artificial intelligence product consultant. It's kind of a new thing, but it's very exciting. I've been volunteering on the Flatbuffers project since 2013. And before the Rust port, I wrote the Go and the Python ports as well. So I've been involved a long time. Just as a sidebar, the creator of the project is actually here tonight. Wouter is back there in the corner. If everybody wave for him, maybe. So what is Flatbuffers? Flatbuffers is a high-performance serialization format. Kind of the key idea is that there are no heap allocations needed anywhere, not for reading, not for writing. It's schema versioned, and it supports a lot of languages, and more are in the pipeline. Right now we have C, C#, C++, Go, Java, JavaScript, Lua, PHP, Python, Rust, and TypeScript. And this is the pull request I'm going to talk about tonight. So this was on GitHub, and we merged it on September 2nd, excuse me. And you can see that there's kind of a big description, got a lot of likes and party hats and stuff, so it was a very exciting day for me. And this is the only place where I show the project GitHub page, so I want to note that we crossed 10,000 stars as this pull request was being submitted, so that's kind of a big milestone for our project. And on my part, this Rust port was a volunteer effort, took 6 months, and just for clarity, I don't work for Google. Let's talk about serialization. This is short, 2 sections. I'll give a definition and then some examples. A serialization format describes how to write and read data, and that's it. There are too many choices to make with this, so you can imagine any number of choices and options to choose from for how you can write data, save it in memory, save it on disk, send it over the network, read it from the network, all these different options. So for concision, I'm just going to focus on 3 different kind of popular ones, and I'll compare them. First, tried and true. We love it, we hate it. JSON, it's a plain text format. We can read it. It's human readable. Out of the box, there's no schema evolution, which means that there's no way to have a standard format and then talk about a structured way to change what the data is. Take away fields, add fields. There's something called JSON schema. I'm not going to talk about that. The third point about JSON is it requires parsing. And when we parse, we don't necessarily know ahead of time how much memory we're going to need. And that means we might need heap allocations. Boo. And if we want to store arbitrary binary data, like a PNG file, for example, we have to do some encoding step to make it fit into the JSON format. So a lot of people do base 64 encoding, for example. Second one I'll talk about is protocol buffers. And this has really had a huge impact on the serialization landscape, as I'm sure most of you know. It's a binary format, so it's not human readable. You can evolve it with the schema, and that's a useful property. It does still require parsing, though. It requires heap allocations to read the data. And unlike JSON, it's binary safe, so you can store arbitrary bytes inside of it. You can store files, whatever you want. And then choice 3 is Flatbuffers. It's also a binary format like protocol buffers. It also has schema evolution like protocol buffers. But unlike that, there's no parsing step. So there's no requirement for heap allocations. And it's also binary safe. So why do we do this? I'll introduce some ideas. Mechanical sympathy is the first one. I'll give an example of how we use integers in these different formats, why you would want to use flat buffers, and probably why you would not want to use flat buffers. Mechanical sympathy. I'll start off with this quote from the Formula One driver, Jackie Stewart. You don't have to be an engineer to be a racing driver, but you do have to have mechanical sympathy. And what he intended by this was that you need to have a gut feeling for the strengths and weaknesses of the machine you're trying to operate if you want to have a chance at using it to its full potential. How many of you have heard of this before, this idea, mechanical sympathy? Okay, not that many people. Yeah, I think it's a pervasive instinct, even if you haven't heard of the term, to know how the machine operates. I make the strong claim that slow software is our fault because the machines are extremely fast. The real speed limits are billions of CPU instructions per second, gigabytes of RAM access per second, hundreds of thousands of SSD IOs per second. So if we aren't achieving that, that's our problem. It's not the hardware's problem. Hardware is great. And I think Rust philosophically is a big way that we can get there in the future where we're not already. What do CPUs want? This is the machine that we want to have sympathy for. Maybe kind of like we want to have an intuition or almost a feeling for it. CPUs want flat array data. They want fixed width scalars to fit in registers. They want aligned struct types. And they want data to be cache friendly, which means it's packed together. Could we have a format like protocol buffers that's binary, statically typed, multi-language, schema versioned, just like protocol buffers, but with the additional feature of being CPU friendly, of being mechanically sympathetic to CPUs? And unsurprisingly, because I'm here tonight, the answer is yes, and Flatbuffers is that format. Is everybody with me so far on the justifications for this? Great. So the key idea behind Flatbuffers, the philosophy in one sentence is, data should be stored on disk the way it is stored in RAM. So here I'll compare 3 different serialization formats, again, JSON, protobuf, and Flatbuffers, and give a concrete example of the requirements for heap allocations in the first 2. So in the left column, you can see that JSON, I describe it below as being an ASCII format, and there's an example, 1, 2, 3, 4. It's a number that's in ASCII. And the way that you get that number into a register in your CPU is you have to parse it. You have to parse it into some variable. Okay, protobuf. It uses this thing called varint, which is a way to save space when you have small integers. So if you have a U32 but only the number 1 is in it, you only use 1 byte to store it. That's a space savings, but the flip side is that because the decoding step is data dependent now, you have to do a lot of branching, and you might have to make allocations to parse that successfully. So you get space savings, but you have heap allocations. And that also is a parsing step, but it's a binary format, so it's a little bit different. Flatbuffers, in contrast, has little endian integers. They're always the fixed size, and the way you access them, let's say you've memory mapped this Flatbuffers object, is you just do a pointer dereference. That's it. It is in the wire format how it should be in the CPU. Some of the use cases for Flatbuffers, RPC calls, write-ahead transaction logs. These are things that in databases, when you want to commit a write as quickly as possible to your database, you append it to a log, and then you'll need to read those in quick succession to update some index or some disk data structure. And so the fewer heap allocations, the less churn you can have, the better. Rendering in UIs, which I'll bring up an example in a second. Video game save files, which was actually one of the initial reasons to create Flatbuffers, because it came from a game library lab at Google. And finally, it's maybe a value format and key value stores, so you can store these in a big index and then pull them out, and you can have the structure be inside the values. So here's one example. Facebook uses it in the Android app. You've probably heard of Facebook. They have a popular product. A lot of people use it. They have over 1 billion users of the Android app. And they moved from JSON to Flatbuffers, and they decreased load time from 35 milliseconds to 4 milliseconds. They reduced transient memory allocations by 75%, and they completely eliminated that really annoying effect of stutter when you scroll. So if before they had it, you would scroll quickly and it would maybe not catch quite up, or it would feel jagged, and now it's silky smooth. So I've heard. And here's their blog post about it. And this was over 3 years ago. So you can see the libraries had some success even before Rust came along, which is shocking, I'm sure. But another use case, so there's a successor in the works to Node.js. It has a different philosophy in a lot of ways. And internally, they still use V8, but they use a lot of Rust also. And they were able to use Rust Flatbuffers, which just came out, and they're actually using our alpha version, which was scary for all of us involved. But they were able to rip out a lot of their C++ code and convert entirely into Rust as a result of using Flatbuffers in this way. They also use Flatbuffers in their TypeScript components and pretty pervasively all over the place. It's not perfect. Shouldn't use it all the time. Couple of anti-use cases that come to mind. If you're storing things like trees, or tries, some people call them, or hash tables, you probably don't want to use Flatbuffers for that. You could probably, but it'd be awkward. Sparse arrays, like we see in machine learning, very large arrays where most of them are zeros, and so you compress it that way. Not a really good fit for Flatbuffers. And because Flatbuffers has a format restriction of 2 gigabytes per payload, if you have huge files like videos, it's not going to be a good fit either. All right, how to use it. As an aside, I like distinguishing between how to use it and how it works. And I've noticed the developer marketing material will conflate the two, like, install our thing, how does it work? It's like, no, that's not how it works. So I'll talk about how to use it, and then I'll talk about how it works, so you get both sides of it. First, I'll show you how to install the flatc program, write a schema, generate code, add it to your cargo file, and then have hello world. So we have Flatbuffers in a couple of different package managers. This just shows you can brew install it, and it works just fine. Second thing is you can define a schema, and I'll walk through it. I apologize if not everybody can see it, but I want to show off some of the different features that we support, especially for those of you comparing to protocol buffers. So starting at the top left, we can declare a namespace, so we support nested namespaces. We have enum types, we have unions, we have structs, which are packed data, and they're actually not schema versioned, but the trade-off is they're very efficient, so you could put them in a big array. Going to the other side of it, we have this thing called a table, which we call a monster, and that's just a game legacy from the beginnings of the project. And this is sort of the prime type or declaration in a Flatbuffer schema file is the table. And so every field there can take a number of different parameters. And going from the top, we have something called POS, or position, which references the struct that we created on the left-hand side. So it's a three-dimensional vector where you could be in space. The next one is a U16 variable, which we call a short, and it has a default value of 150. And so the default values are really important because if you know ahead of time about default values for your data, you can save a lot of space. Going down, we have strings, we have default values for bools, which we can deprecate any field. We have a vector of bytes, and that's useful as a generic type. Enum, default values, and so on. Okay. So we can use this file with the FlatC compiler and the Rust flag to generate generated code. And what comes out is a pretty big file relative to the amount of data we put in the schema. So this shows that the generated file is about 500 lines, but it contains everything we need to read and write data in many different scenarios. To use it in your code, after you've generated the code from the compiler, you should add this to your cargo.toml. We're currently at version 0.50. I'm sure there'll be a quick progression of versions throughout the next 12 months because this is still an early stage port. And this is the hello world. Pardon the width of it, but I'll walk through it line by line quickly. So on the first line, we import the crate, which includes the runtime code. And so these are all the common functions that the generated code can call to get work done. And we load the monster generated file manually using a declaration that says the path is here. We import some things from that generated code. And then on line 8, we create what's called a builder, where this sets up the state needed to create a Flatbuffer object. And then we use that builder. On line 9, we say monster create, and this was a function created by the code generator. And it takes a builder, and it takes something called an args struct, which is a way to encapsulate the arguments you need for that particular table. And you remember the schema file had all these things in there that were, I don't know, maybe 10 fields. But here we're only giving something called HP. And that's because in this Rust code, the arg struct takes default values. And so that was an important ergonomic development that happened pretty late in the port. On line 10, we finish it, which means we just sort of wrap up the bookkeeping for the buffer. And then on line 12, we extract the bytes. So now this is just a U8 slice. Line 14, we initialize it, so we read it as if it came in off the disk or off the network. And then finally, on line 15, we can call it as a Rust object we call monster.hp function. And what that does is it makes the traversal necessary inside the data to find the value of HP. If it's not there, it might give us a default value. If it is there, it'll give us what we expect. And in this case, it should be 80. Everybody with me so far in the hello world? Great, okay. So this is the more interesting part to me as the implementer. So now we're going to get into how it works. And we're probably 2/3 of the way through the talk, maybe halfway. So I want to focus on 3 traits that really helped us write good code for this. The follow trait, the push trait, and the SafeSlice Access trait. Follow and push are 2 sides of the same coin. Follow is for reading and push is for writing. SafeSlice Access is an optimization. So the follow trait works because Flatbuffers are tree-shaped. And we have this thing called offsets, which are like pointers. They're always 32 bits wide, but we interpret them in the same way. So it tells us where to go inside of a buffer as we traverse the data. And what's interesting about the follow trait is that it allows us to interpret these offsets as type system entities. And so in this way, conceptually, the follow trait lets us lift these effectively pointer dereferencing actions into the type system. So here's the definition of the follow trait. It's in the Flatbuffers crate. And you can see we have one lifetime that we give it. We have an associated type called inner. And then there's just one function that's called follow. And it takes a buffer, which could be very wide, and that takes a location in that buffer. And that location, that buffer, is our offset or our pointer. And then what it returns is the associated type self inner. And so by having it return what the associated type is, and then maybe that also could have an associated type, it could be follow too, or it could be follow, and so on, we get this, I'll show you in a second, a declarative chain of pointer dereferences. So this is a pretty hairy function definition, but the signature is as long as the function, so that's kind of nice. But the thing I want to point out is that on line 2, this get function, which is used pervasively in the code, this is in the runtime library, and it's called in hot loops all over the place. It has a trait bound of follow. And what this means is that T needs to be follow. And so that means T needs to be dereferenceable. But this function doesn't know how to dereference it. It just calls follow on line 11. The things in between, lines 7 through 10, are what allow us to get default values, and that's kind of intermingled with the generated code as well. So here is how it looks in the generated code. It's a simple example, and we used HP earlier, so I'll show this again. So here we have a function marked inline, and we call it HP for health points. Then it returns an I16, and here we see self.tab.get, and get was the function we just had in the other slide. But now we give it a hint. We tell it what is the type T that should have follow on it. Well, type T is I16. And we go find it in the flat buffer at offset monster VTHP, which is a generated constant. And this is part of the interplay of the generated code and the runtime code. And there was a lot of architectural decisions that had to be made to make that sane. Sum 100 is the default value, and then unwrap is there because we always know it will exist. So in this example, I16 has follow implemented. So what that means is that at VTHP offset, there's code to pull out an I16 at that lock, LOC, in the buffer. But here's a much more fun example. So this is test array of string, and this is a different example in our test suite. So here we're talking about a vector where each element is an offset into a variable length string. So it's actually a pretty complicated data structure to serialize. But we encode this in the type system. I'm not going to walk through it manually here, but every step that I mentioned about the vector that could be variable length, and inside those, the offsets to these things that could be variable length, those are all in the type system. And so that has made programming this to be much more fun, and also it feels like the compiler has my back in a way that maybe we wouldn't have in the C++ versions. So I find that to be a significant innovation for the support. Any questions so far on all that? Okay, cool. All right, second trait, push trait. This is the right dual of the follow trait. And so this is a little more complicated, but the thing that's important is on line 3, we have a function called push, and it takes in, or it is the function where a type that implements it will know how to write itself into a buffer. And then there are other things about sizing, alignment. And so this is a way for a type to sort of export everything that is needed to write itself to a buffer. And we use it pervasively, again, in the runtime library, this time in the builder path, the write path. And here we have one function, it's called push, and it takes a type P, which has a trait bound push on it. And you can see that X has type P, and then it returns something called a work in progress, or WIP offset of type P output. And so this is the flip side of the follow trait, where we had the input as the return value, return type. This we have the output, and so there's a real dualism there. So the key thing is on line 8, where we do x.push. And that is calling the implementation of push that X has. And so this is a way to keep the code in the write path very small. And the generated code contains implementations of this for all the types that need it. So here we have a type that is like the XYZ coordinates that we had earlier. So this is called vec3, and so you can see it's implementing the trait Flatbuffers push for vec3. It declares an output, and this is what I would call a terminal type, or a terminal push implementation, where it's saying for the type vec3, here's how you get a vec3 as output, and that's just an artifact of how we use these as types to do the traversal. And so in this case, push is using an unsafe operation to quickly memcopy itself to the provided byte buffer. As an aside, we know we can do that safely because in Flatbuffers, most data is little endian always. And so even on big endian machines, we store it in RAM as little endian, which means we can memcopy it as little endian onto the wire when we need to. The last trait I'll talk about is SafeSlice Access. So this is just a dummy trait. It indicates that the host machine is little endian, and it lifts endianness into the type system. I hope that's a theme you can see. I'm trying to lift everything into the type system. Maybe I went a little overboard, but I think it was a good idea. And so when this type checks, it means that it's safe to use memcopy to copy data from, say, a vector of bytes or structs or whatever directly into the byte buffer of the builder, the write path. Essentially, it makes the write path much more efficient when it can be by using memcopy everywhere it can. The alternative on big endian machines is that it'll use different operations and might write byte by byte, for example. Okay, testing. So we test in 5 plus a bunch of different other ways. So we test for C++ and Java compatibility. We test that the code is importable. We do a lot of fuzzing round trips. We count heap allocations. We check bytes on the wire. And then we have a bunch of miscellaneous ones. Testing, C++ and Java. So Rust is the 12th language to be ported to Flatbuffers, so we wanted to make sure we comply with the things that came before us. So we could agree with the format in theory, but we also needed to agree with it in practice. And so some of the tests in the test suite will load C++ and Java generated data and check that they can read it. So here's an example from the test suite. You can see on lines 2, 7, and 12, we just have these different checks for C++ and Java in a couple of different situations. And they're all calling the same function that checks that a buffer has the right data that we expect it to. And the way the test suite works is that we have a schema that all the test suites use, or all the language ports use to test themselves. And so we can have these common data payloads that we send between the language ports to check for correctness. Second thing, testing imports. Generating usable code can be tricky. I mentioned that there was kind of a big blow-up factor when we're generating code compared to the size of the schema, and getting all that right with namespacing and modules and public and private types and lifetime constraints can be error-prone. And so to just absolutely make sure that that's working as we need it to, we take a black box approach to testing. So in our test suite, the entire test suite file, which is thousands of lines long, we begin by importing our generated code using the same way that you would as a user. So we extern our own crate and we load in the generated file using the mechanism that you've seen a few times throughout the talk. Third thing, fuzzing round trips. So Flatbuffers is a library for reading and writing data. So what are all the cases we could test? You can't really test all cases because the users are providing the input. And so we use an approximation of all input called quick check, which tries to create exemplary test cases that we can use to test a wide variety of edge conditions. And when there's an error, quick check will hone down and find sort of the minimum violating example so that it's easy to debug. So we use that all over the place in the test suite. Third thing, counting heap allocations. In theory, the Flatbuffers format doesn't require any heap allocations, but do we actually do that? Maybe we have a vec hidden somewhere, something like that. So as of Rust 1.28.0, we actually can use a custom global allocator in a separate program to verify that we aren't making any heap allocations on hop paths. And so this is the critical section. So on line 1, we're creating a static global variable called n_allocs, and it starts off at 0. We follow just the documentation for creating a basic allocator here. So 2 is tracking allocator is our name for it. We implement one function on it, which returns the number of allocations that it has seen so far in the program. And then on lines 10 through 18, we implement pass-through functions for allocation and deallocation, with the caveat that on the allocation path, we increment that global n-allocs variable. And then at test time, we pull out the n-allocs value and assert that it has stayed the same as it was before the test was executed. And so this is how seriously we take performance in the Flatbuffers project, that we're trying to use features as soon as they're put into stable to make sure that we're as fast as we possibly can be. I'll talk more about speed and maybe the potential for that later. The next test, bytes-on-the-wire. So Rust code should generate exactly the bytes we expect. There's technically a little flexibility in how the different ports can create data, but we try to stick to the common ways that it's been done before for maximum sort of bug, being able to sleep well at night, that you don't have bugs in your code. And also, these tests are really good for new contributors because you can see concretely what the byte layout is on the wire format and kind of bridge the gap between the schema, the generated code, the runtime library, and then finally what is on the wire, what's on disk, what's in RAM. So here's an example. The idea is that it's a test function that stands alone, and there is one utility function called check. And so lines 3 through 7 create data. They set up some situation in all these different test cases, write some data, and then we're done writing, and on lines 8 through 16 we call this check utility function that verifies that the data that was written to the byte buffer is exactly what we expect. And so in the comments there are actually often descriptions of what the numbers mean. And so that's an implementation detail of the format itself, but if you're interested in getting involved in the project, this serves as a very precise form of documentation. Miscellaneous testing. We have 191 tests in the test suite and growing. We test data alignment and sizing. We check various borrow checker situations. So for example, we had an issue recently with Flatbuffers that were used with data that had static lifetimes that wasn't working, and so we fixed that, and now we're checking it in the test suite. We have many tests for the different major types in Flatbuffers, such as tables, structs, vectors, unions, enums, scalars, and also many tests for the traits that I mentioned earlier, including follow and push. Finally, future work. There's a lot still to do. First thing is that we would like to implement what's called a verifier. So Rust, C, and C++ and Flatbuffers are unique because they are able to do unsafe things with memory, which in Rust land we don't really like, but in this case we can justify it if we can implement a verifier that uses an already known algorithm to double check that the offsets don't go out of bounds. And that's a very quick process, and we know that from C++ already. And so once we can have that in Rust, then we're free to do even more aggressive unsafe usage because we know it won't go out of bounds at runtime. And this also lets you use untrusted data. The second thing is that Flatbuffers has support for the mutation of values. So if a space is already allocated in a buffer, then you can overwrite those bytes with a value that fits. And the Rust port does not yet support that, but we hope to soon. The third thing is reflection. So in the C++ port, it's possible to evaluate metadata at runtime. We'd like to be able to do that in Rust as well. 5, extreme fuzzing. This one's pretty exciting to me. As you can tell, I like testing, so this is the next level. Extreme fuzzing would be a situation where we can generate whole Flatbuffer schemas randomly, maybe using quick check. We can generate data that complies to that schema that we haven't seen before, serialize it, deserialize it, and then check that the values we get out are the same as what we put in. And so that would be a complete round trip from write to read. And then there's something else we could do where we go even further and we do writes and reads through all these different languages and make sure that the game of telephone comes back how it should be at the beginning. And then finally, 6, we haven't really done any benchmarking, no real attempts to speed things up in a rigorous way. We're already pretty fast, but I think we can be a lot faster. And so this is just the beginning, and if you all are willing to dig in, we have a lot of really helpful mentoring maintainers and contributors, and I hope you take a look at the project. 3 final thoughts. 1, there are network effects with serialization formats. So the more people who like it, who use it, who are happy users, the more people who use it for storing data, the more people who use it for sending and receiving messages. The network effect there means that the format will grow in usage. And that's one of the reasons that it's hard to dislodge existing serialization formats. It's like the social network of data storage. So we hope to make users happy so that we can grow. The second thing is that Flatbuffers, to me, represents an optimum where it's got the features of protocol buffers, but it's also got mechanical sympathy. It's CPU friendly. It has all these properties that make it very fast, and I would argue probably as fast as it can be for what it provides. And then finally, and I know my audience, so I think that Rust and Flatbuffers have the same values. And that's to be very careful with types in memory to achieve safe, zero runtime, high-performance software. Zero overhead, high-performance software. Thank you. Any questions? Yep.
So-
Do we do the mic thing?
Yeah. So you said hash maps aren't a good pattern?
You could probably figure out a clever way to do it. It's not
Okay.
something we support.
Because, half my structs have hash maps.
Right.
What about hash sets?
So the way I'll answer that is that I believe the C++ port supports this, and maybe Wouter can speak to it. But there's limited support for a key value
Okay.
operation, which might be what you need.
Yep. Okay.
And then you can deserialize it how you want in memory. And I'll just note that whatever the hash map or hash set that you're using, that doesn't map to what the wire format would be. It's not necessarily memory mappable.
Yeah, I don't care about that so
Yeah.
much.
Yeah,
But just being able to use it.
sure.
So the C++ port and some other ports, thank you. They support in-place binary search, so it's not a hash map, but certainly for doing some kind of dictionary kind of structure. And the cool thing is, like much of the rest of Flatbuffers, like you don't actually have to build up a binary tree first. It works directly on the stored data. So if a binary tree search is fast enough for you, then this will be a great solution.
Why should we use Flatbuffers instead of the Rust port of Cap'n Proto?
This this comes up a lot. We like the Captain Proto project. I think that there are uses for both of them. In my estimation, and I'm not an expert on Captain Proto, and I am on Flatbuffers, so I'm biased and I have a biased knowledge base. But some of the things that I understand Flatbuffers give are one of the major things in Captain Proto is this idea that there are a lot of zeros, and so you can do run length compression of zeros on the wire, and that's beneficial. And it is if you're willing to decompress your data on the other side. But the whole premise that we've been talking about is that data should be okay as is. We want to memory map it, we want to load it with no overhead. And so if you take away that extra decompression step that Captain Proto sort of requires to get a lot of those benefits, that's one example of how Flatbuffers might be preferable. But again, I don't want to speak too much to it because I'm not an expert in how to compare
I just
them.
have a comment on
Yeah.
Cap'n Proto. Okay. Cap'n Proto is, the cap in Cap'n Proto is capability, so it's capability friendly.
Speaking from personal experience using the Cap'n Proto Rust port, it's got a lot more error checking going on. So if you're actually dealing with the buffers, this looks a lot more friendly to actually using flat buffers. Like if you're writing a game, this looks a lot more friendly to actually using flat buffers to store parts of your game state, and so making it easier to save that to disk. But if you're using Cap'n Proto, it's not so friendly to that. If you're reading from it, there's a lot of error checking to go on when you're actually taking out values, and so you find yourself doing a lot of unwraps on your own. From what I've seen, for example, in the .hp call, it does the unwraps for you. So it seems like it would be a lot more convenient to use in that particular case.
So you're talking about developer ergonomics with that?
Yes,
Yeah.
which is very important to me.
I want to give a shout out to the creator of Cap'n Proto because my understanding is that he was crucial in creating protocol buffers, and we owe a huge intellectual legacy tradition to that. So I don't really see it as a competition. I see it as an ecosystem where we can learn from each other. Not to be too diplomatic about it, but you know.
For what it's worth, I use cap and proto with an additional essentially parsing step. I'll actually extract things and then turn that into my in-memory structure rather than just using it in place
Okay.
because of this. So if that fits your use case, then so be it.
Great.
Do you have a lot of examples of people using flat buffers for FFI between two languages? Rust and Python, for example?
The only major one I know of is the Deno project that I mentioned earlier. So they're using it to, so they have a runtime that's in Rust and C++ and also TypeScript and JavaScript or something. It's pretty complicated, but to make all that tolerably efficient, they use flat buffers as the RPC in these very hot loops between things. Besides that, I'm not familiar with many other projects, but I bet they're out there. Oh, and also, bigger picture, gRPC added support for flat buffers I think in Go. So that's an example of cross-platform usage. It's pretty major.
You mentioned checking for allocations in hot paths. Is that to imply you still have allocation happening in other places?
There are 3 ways allocations can happen in the write path. The first one is when the builder itself has a set of bytes that it uses as scratch space. When that is at capacity, no more allocations happen. So it will regrow and then you can reuse that data over and over again. No more heaps in steady state operation. The second way is that we have a utility function called create vector of strings. And I mentioned earlier that a vector of strings is a bunch of variable length, nested variable length data. And so inside there we use a package called smallvec, which unsafely puts vectors of things on the stack if it can, and then on the heap if it can. And so that's the place that heap allocations can occur. The third way is through you creating data. So the references that the builder gets, they need to come from somewhere. And so if you make a string, for example, that might be heap allocated. And so at that point, if you're creating things in a hot loop along with the Flatbuffers code, it's not technically Flatbuffers' problem, but it is your problem. And so it's part of the same situation. Does that make sense?
Yeah.
Yeah. Also, I'll say on the read path, there really are no allocations required. I can do this all night. Really excited about serialization.
We're good. We're good.
Good.
Thank you. This is a really awesome project, and I'm really glad you brought this to Rust. I missed a few of the questions, so this might have already been covered. But I saw that during writes, you like to use mem copies whenever you possibly can. You showed an example of mem copying an entire vector at once. And I'm wondering how Flatbuffers accounts for padding in structs, whether it thinks about that and does anything special for it.
So one cool technique about implementing this was that actually gets handled by the FlatC compiler. So when it emits code to describe a field in a struct, for example, it'll say field A is a U16 or whatever, and the next field is whatever. And then it actually outputs manually. They have underscores at the beginning and they're not for users to use, but we actually have the padding defined explicitly in the struct type.
Cool.
Yeah, and that way we're not leaving it up to, what are they called when you have the pound sign and then above a struct, those attributes? We're not leaving it up to that.
I noticed that in your generated code examples, you have a lot of inline attributes. Did you find that it's often necessary to add those, or do you just add them just in case?
So I started off without them because there's this idea that LLVM is sufficiently smart. And I'm not a compiler expert, but I know somebody who is, and that's Wouter. And one piece of wisdom he gave me is that when you start suggesting inlines, note that I don't say inline always, I just say inline, so it's a suggestion. When the compiler starts agreeing to those suggestions all over the place, it can start collapsing code together and start doing optimizations that have a compounding effect. And so I anecdotally noticed that when I added inline to all those things, and all these different places where they can show up, generated code, library, all that stuff, that the runtime's sped up quite a bit. Sometimes even doubling in speed from, say, like 500 nanoseconds to 250 nanoseconds or something like that. Cool.
You should basically never be using inline always in Rust. You should basically never be using inline always in Rust. It slows down compile times, and usually Levien is smart enough. There are very few cases where you actually need it. Inline can't.
I'm nervous every time now.
So Rust is interesting in that the string type guarantees that your data is UTF-8.
Yes.
Flatbuffers looks like it has a string type. How is that interop handled?
So I believe that when we implement the verifier, we'll be checking that. Is that true?
We don't in C++. So
Okay, but we could do that in the verifier.
it's specified, it's supposed to be UTF-8, so
Gotcha.
there's probably ways around that.
Yeah. So that's a really good point. The way that it's handled in general in the project is that the language natively that writes the data should know that it's a UTF-8 string, and so it should be writing correct data. And then so on the read side, we can, assuming that you trust the source, can just cast it to, say, a UTF-8 string. But yeah, I think you just gave us another feature to work on for the verifier.
Here we go.
Thanks. Were you able to use some interesting things with like borrow checker? So Flatbuffers, like you essentially have memory, view to data. So like you could do mirroring or like without even copying. Like it seems that, for example, if I want to pull a string from the Flatbuffer, I'm still actually, do I get a slice of it or like do I copy the bytes? Do I get a view on it?
So the slice descriptor, the reference and the length, that is copied and put on the stack. But the memory that it points to is in the flat buffer, and that's done unsafely. Does that answer your question?
Yeah, that answer is. And how does it work with like the fact that you want to make flat buffers mutable later?
Oh yeah. So I haven't added that to any of the ports, so I'm not an expert on it. My understanding is that we would have to have probably quite a bit of separate code paths where we add mute to things to allow users to change data. In other languages, it's easier. Like in C++, you can just get a pointer and there you go. But here we need mute and non-mute references. So that's still TBD.
Mm-hmm.
And again, if you all want to begin contributing, these are cool. These are great.
And like for simpler types, like integer, would it be also pointing to exact same memory, or would you actually copy it? Just curious.
So because the pointer would just be pointing to the buffer that stores the flat buffer data. I'm using buffer twice. I mean the U8 buffer that backs the flat buffer data. So you get a pointer into that, and you know that at that location there are 1, 2, 4, 8 bytes that represent some number. And so on the read path, we just if you're on a little endian machine, then you just get that value directly, just a pointer dereference. But if you want to write to it, that means you can just do, in C land, you would just do a dereference equals to set that to a new value in that memory. And then to persist that, you would just copy